Welcome back. In this video, we'll do a couple more examples of finding linear equations of exponentials using the semi-log system here. And we'll do one with base 2, we'll do one with e and involve the natural log. Then we'll also use our calculator and the table value and put values into a table, and also use our calculator to find a linear regression model of a semi-log plot. And then finally, we'll look at a couple of tables and data and select a potential regression model. So looking at example 3, it's going to be very similar to the example we finished the last video on. We're given a function 8 times 2 to the 2x. So we have an exponential here in base 2. Find the values of m and b such that we have log base 2 of g of x, and we linearize our exponential. And then we'll graph that on the graph paper provided, and it's also asked us to label the axis appropriately. So our y-axis is log base 2 of g of x. We can actually steal that right from our y equals mx plus b, and then our x-axis, of course, is x. So we begin by just writing down our function, 8 times 2 to the 2x, and then we're going to go ahead and log base 2 both sides. So now I've log base 2 both sides, and on the right-hand side, I'm going to apply my properties of logarithms and do some simplifying of the right-hand side. So we're going to invoke the product rule and the power rule and simplify that. So I have log base 2 of 8 plus log base 2 of 2 all raised to the 2x. So I'm expanding my logarithm on the right-hand side. Log base 2 of 8, we all know that's 3, plus 2x, because I invoke my power rule and bring that 2x, that exponent, down in front. Log base 2 of 2, which is 1, and I get 3 plus 2x, or in slope-intercept form, we get our y, or log base 2 of g of x, equals 2x plus 3. So we have a y-intercept of 3 and a slope of 2, so I can rise 2 and run 1, and rise 2 and run 1, and then go ahead and graph. In example 4, we're asked to linearize h of x equals 5 times e to the 7x over 3 and find the values of m and b so that our h of x is also a linear equation. So since we have e, now we're going to use the natural log, but still our same properties of logarithms. So in the first step, I natural log both sides. On the right-hand side, I have the natural log of 5 times e all raised to the 7x over 3. And I'm going to apply my properties of logarithms and expand that logarithm. So I expand that logarithm with natural log of 5 plus the natural log of e all raised to the 7x over 3. I'll apply my power rule and bring the 7x over 3 down in front, and the natural log of e is 1, so that drops out. And my equation becomes 7/3 x plus the natural log of 5. And now I've got the natural log of h of x, where m is 7/3 and our b is the natural log of 5. That also would be our y-intercept, 0 natural log of 5. And the natural log of 5, you could put that in your calculator, and that's like about 1.6094. Speaking of your calculator, you're going to want your calculator for example 5. We're going to use the table value, the tables. We're going to use the stat and find a regression. So we're going to have some really good calculator stuff in example 5 here. A says, find the natural log of y and plot the data t natural log of y on the grid provided. So in A, we're given some t values, which we would put into our function. and we'd get these outputs of 3 and 8.2 and so forth. But remember that our y in our semi-log plot is the natural log of y. So we're going to want the natural log of these values that we've output in our function. So think of a composite function. We want the natural log of 3e to the 0.05t. So really what we're looking for here is the natural log of 3, the natural log of 8.2, and so forth. Well, what I've done is I've put the two functions into our calculator, the original 3e to the 0.05t, but I've also done the second column as well, which is the natural log of 3e to the 0.5x, and that's going to actually give us the third column. That's going to give us our outputs that we want. I put in my calculator 3e to the 0.5x. My outputs will be column 2, and then I'm going to use my outputs from column 2 as my inputs to create column 3. I put my two equations in, and I can go to second table set, and I'm going to start my table at 0, and I'm going to count by 2s because I see my table's got all even numbers. And I go second table, and it will give me not only my second column, but it gives me all the values I need for the third column. For 0, it's 1.0986, and 2 is 2.0986, and 4 is 3.0986, and 10 is 6.0986, and 20 is 11.0986. So let's go ahead and record those on our notes. So my natural log of y, which really is the natural log of 3, 1.096, 2.096, and so forth. And I put in this column here. Really, how did I get that? I did the table, or I did the natural log of 22.2. And then we're asked to plot this on our table here on our coordinate plane. So I plot my t's, or my x's. My y's are the natural log of 3e to the 0.5t. So those are my y's. And we can see here that looks like a scatter plot that is linear. And then now we're asked to use our calculator to find the linear regression. I'm not going to do this by hand. We'll just use our calculator to find that. So I'll go back to the stat menu in my calculator, edit. I'll put my list 1 will be my x's from, or my t's from 0 to 20. And my list 2 will be my final column, my y's, which is the natural log of y. So I put all those values in. I've got those. Go back to my stat menu. We'll do calc. We're going to do a linear regression. So 4. I'm going to use list 1 and list 2, it looks like. Maybe I better store it in y4. And we'll calculate that. And we get a slope of 1/2 and a y-intercept of 1.0986, which shouldn't surprise us. Take a look at what we got here. So I'll set my window based on my x's and my y's and that I've given in this problem. I'll graph the y4, and there we get a nice looking graph. I probably could put my points on there. We'll turn that plot one on, and look at that, a nice graph right through those particular points. And I'll copy down my regression model, and let's go on to the next page. In example 6, we want to select a regression model. It says, consider the data in the tables below. Determine whether the data can best be modeled by linear, logarithmic, or exponential regression equation. Explain your choice. Support your answer with tables and graphs. Let's take a look at our differences in A, and it looks like our differences are 3 in each of these. So we know if our differences are constant, this is a linear regression. And going back to probably unit 1, we know if d is 3, we have a slope of 3, and we can subtract 3 from our y's to find our y-intercept, and our function here is going to be y equals 3x plus 2. In example B, let's look at our differences. 6 to 12, 12 to 24, 24 to 48. So our differences are doubling. Our change in y is a factor of 2. This is an exponential function. So our function here is y equals 3 times 2 to the x. So when x is 1, we get 3 times 2. When x is 0, we get 3. So we would know that the 0th would be 3 here. In example C, we're increasing by 1.4, then we're increasing by 0.8, then we're increasing by 0.6. So we're increasing at a decreasing rate. We've got something that's concave down, and that is logarithmic. And a logarithmic graph, right, a function goes through, our parent goes through the point 1, 0. This one, when x is 1, or our answer is 1, we're going through 4. So this has actually been shifted. Well, our y value is 4 instead of 0. So this has been shifted 4 units up. So instead of 0, we have 4 here. So this is a logarithm that's been shifted 4 units up. My answer key tells me this is y equals 2 times the natural log of x plus 4. So there's our shift of 4 units, but apparently there's some doubling here as well. We might want to explore that in class. And in sample D, our differences here, we've got 1/2, and we got 1/2 again, we got 1/2 again. This is a geometric sequence or an exponential with a base of 1/2. So it's exponential, our base is 1/2. Our function would be 1/2 to the x. When x is 1, we need 1/2 to get to 13, so we need our b value to be 26. So when x is 1, when x is 0, we get 26. So sure enough, the previous number would be 26. And that looks like that one's going to work as well. So that wraps up this video with more examples of using semi-log plots, exploring logarithmic functions, using our calculator. Lots of good stuff in here. And we'll get some more practice with this when I see you in class.